Hi, you guys. I have another problem today, and it's a forces problem this time, as it has been for the past few weeks, maybe a month or two. But anyways, before we actually get started on this problem, if you don't mind, please don't forget to like and subscribe. If you find my videos helpful, if you don't, then I'm sorry. I hope you find something helpful. But yeah, if you find it helpful, please don't forget to like, subscribe, and share with your classmates and friends. Okay. Also, I've created an Instagram account, so if you want me to start posting on there, feel free to follow. And if I have enough feedback, then I'll go ahead and start posting on there as well. I have some ideas of what I would like to do. So yeah, let me know. And as always, you're always welcome to email me. Okay, so problem 4.48. These are problems as usual. Well, this problem, as every other problem, is from Young and Freedman's University Physics textbook. Okay, so this problem is called extraterrestrial physics. You have landed on an unknown planet, Newtonia, and you want to know what objects weigh there. When you push a certain tool starting from rest on a frictionless horizontal surface with a 12.0 Newton force, the tool moves 16.0 meters in the first 2.00 seconds. You next observe that if you release this tool from rest at 10.0 meters above the ground, it takes 2.58 seconds to reach the ground. What does the tool weigh on Newtonia, and what does it weigh on Earth? This is a really interesting question. This isn't like the past few problems we've done. This is going to be a little bit different. And this is really an experimental problem, right? So we can see in this question that we are performing two experiments. First, what we're doing is that we are pushing a tool from start to finish, and we have the force, the distance it travels, and how long it takes to travel that distance. Next, we release this tool from above ground 10 meters and measure how long it takes to reach the ground. Okay, so we need to use these experiments to figure out what exactly the weight of this tool is. Awesome. So let's go ahead and let's write down all of our knowns. So like we said, there's two experiments going on here. There's going to be experiment 1, right? And I'm just going to go ahead and highlight it. So you push a certain tool. Oh, sorry about that. Let me just, I thought that was a highlighter. Okay, so let's go back and let's write down all the information that we have. So we have the initial speed, right? And that's going to be 0 meters per second because it starts from rest. Then we know that we push with 12.0 newtons of force, right? And then we know that the distance this travels is going to be 16 meters, 16.0 meters, and it takes a total of 2.00 seconds. In the first, well, it didn't take a total of 2.00 seconds. The tool moves 16.0 meters in the first 2.00 seconds. So that's what's relevant to our experiment. Could be more, but we're not looking at that. Awesome. Okay, so next we have experiment 2, right? So what's the relevant information from experiment 2? Release this tool from 10 meters above the ground. It takes 2.58 seconds to reach the ground. Okay, interesting. So what we know is that the total distance or the displacement of the object is going to be 10 meters, right? Minus 10 meters, because let's say that up is positive and down is negative. Okay, how long does this take? it takes 2.58 seconds to reach the ground. And also just going to do that for sake of consistency. Okay, so it starts from rest. So that's going to be VI is equal to 0 meters per second. Awesome. Okay, so what are we looking for? We're looking for the weight of the tool. So if we are looking for weight of the tool on Newtonia, right? So that's going to be the mass of the object times the gravity of Newtonia on planet Newtonia. And then it's going to be we're also looking for the weight on Earth. So that's going to be force of gravity. It's going to be mass times force of gravity on Earth. And that's going to be its weight on planet Earth. Awesome. Okay, so if we are looking for this, that means that we need these two values. So let's start off with our first experiment. In our first experiment, we have VI, we have the force, we have displacement, and we have the time that it takes. So we know that VI, D, and T, that is going to give us the acceleration of the object, right? And we know that the force is equal to mass times acceleration. So if we want to find mass, we have to solve for mass in the first experiment, right? Then in experiment 2, what do we have? So because this is a typical, typical start from rest, goes 10 meters, starts from rest above, an object starts from rest 10 meters above ground, and then we're measuring how long it takes to reach the ground. Well, we're given 3 pieces of information, right? So the displacement, the time, and the VI. And what we are going to solve for here is going to be the acceleration due to gravity, right? And that's our second piece of information. So that's going to be acceleration on Newtonia. So let's figure that out. Okay. So let's go back to experiment 1 now that we've sort of figured out what we have, what we're supposed to do, the analysis. Okay, so let's solve for acceleration using experiment 1. So acceleration, and we need to use these values. So how do we get that? So we can use one of our kinematic equations that has all 4 values. So we can say that d is equal to v naught t plus half of at squared, right? Because that gives us, we have time in there, we have distance, we have initial speed, and this goes to 0 just because this is 0, right? So d is equal to half of at squared, which means that 2d divided by t squared is equal to a, which is 2 times 16.0, right? Divided by 2.00 squared, and that is equal to 18 meters per second squared. And I'm just going to double check that in my calculator. I'm going to double check that using my calculator. Sometimes I just forget how to speak English. Awesome. Okay, so 8 meters per second squared. That is our acceleration. That's our acceleration for this experiment. Now, since we have force already, right? We have force already. That's going to be 12.0. And we need the mass, and we have acceleration. So it's going to be mass times 8 meters per second squared, and 12.0 divided by 8 meters per second squared is equal to m is equal to 1.5 kilograms. So that is the mass of this object, right? So the acceleration is 8 meters per second squared, and the mass is 1.5. kilograms. So I'm just going to go ahead and erase this part and just write it down in our knowns. I'm going to write it down in blue. Okay, so acceleration is going to be equal to 8 meters per second squared, and the mass is 1.5 kilograms. Awesome. Okay. Okay, so next we have experiment 2. In this one, we are, again, releasing this tool from a height of 10 meters above the ground. And it's going to take 2.58 seconds to reach the ground. So again, in this problem, all we really need to solve for is gravity, right? Because these 3 values are going to give us acceleration, and the only reason this is accelerating is due to gravity, right? Because if you drop something from 10 meters above ground on Earth, the only, thing that's accelerating the object is gravity. So on a different planet, it's also going to be gravity. It's just going to be different gravity depending on what that value is, right? Okay, so again, we have these 3 values and we're going to find what acceleration is. So we're going to use the same equation as last time because it has the same kinematic equation as in experiment 1, just because it has all the values that we need, right? So it's going to be the displacement is equal to v naught t plus half of a t squared. I don't really have to draw this change because it's implied. Okay, so this is going to be canceled out because, v naught is 0. Again, d is equal to half of at squared. And acceleration is actually gravity on planet Newtonia, 2 times d over t squared. And that is going to be 2 times negative 10 over 2.58 squared. I'm going to plug that into my calculator. And that gives me minus 3.004 meters per second squared. And that makes sense, right? Because it's going to be minus because that's what gravity is pulling you down, right? Back to the ground. I was going to say Earth, but this isn't on Earth. This is on planet Newtonia. So it's going to pull back down to the ground, which makes sense. So that's where our negative value came from. So now we have gravity on planet Newtonia is equal to minus 3.004 meters per second squared. And now we have our gravity on planet Newtonia, we have our mass, and the only thing that's left that we need is gravity on Earth, but we already know that. That's a known, right? So I'm just going to go ahead and write that down as well. So it's going to be gravity on Earth, we already know is minus 9.8 meters per second squared. Awesome. So now all we have to do is plug in our values for FGN, right? So how much does the tool weigh on Newtonia? It's going to be FGN is 1.5 times minus 3.004 meters per second squared. And that is going to be minus 4.507 newtons. And then it's going to be for FGE, force of gravity on, the weight of the tool on Earth, it's going to be 1.5 kilograms again, right? But this time minus multiplied by minus 9.8 meters per second squared. Okay, 1.5 times minus 9.8. It's going to be minus 14.7 newtons. Awesome. So this is what we have for our weight on Newtonia and weight on Earth. It's weight, so let's write that down again. FGN, weight on Newtonia is going to be minus 4.507 newtons, and weight on Earth is going to be minus 14.7 newtons, right? So it's going to weigh different on each planet, remember, because mass is always the same everywhere, but gravity is different. And that means weight is different because weight is gravity times acceleration due to gravity times mass. Awesome. Okay, so that is our solution for this question. If you have any questions, comments, concerns, you can always leave them in the comments or you can send me an email. And please don't forget to like, subscribe, and share if you haven't already. And if you thought this video was useful, thank you so much for watching and see you next time.